Hi, and welcome to Unit 4. In this unit, we're not learning anything super new. We're just applying the things that we've learned in previous chapters into new contexts. Well, just into context. And rather than solving for just sort of an analogous x for whatever that is, we're actually going to be looking at specific instances where we are needing derivatives to figure out what's going on. Couple quick reminders. If we want instantaneous rate of change, this is our definition for our derivative. Just a quick reminder of that definition. You also want to think about that in relation to average rate of change. Average rate of change is just the slope between 2 points. Velocity is the first derivative if we're doing like a change in position function. So there were a bunch that we've done before where there's this particle moving around. That's our base function. Then when we take the derivative, it's the velocity of that particle moving. And then a second derivative is the acceleration of that particle. So let's do one of those. So we've got this particle moving along. We want to find the displacement during the first 5 seconds. So that's really just saying, okay, 5 seconds later, where is it at? And all that is asking us to do is to evaluate the function at 5 seconds because we want to find its displacement. Well, I got an extra s up there. So we just need to find s of 5. No derivative, no calculus, just good old algebra. Plug it in and let's see what we got. So let's see, we get 25 minus 15 plus 2, which is 10 plus 2, which is 12, I believe. 10 plus 2, yeah, 12. Cool, done, easy. If we want to find the average velocity during the first 5 seconds, we need to figure out, okay, well, what is the slope between the 2 points of 5, 12, and where it started? So at time 0, where was it at? You can kind of plug that in real quick. Up here, 0 and 0, those are both 0. So it's at 2. So we just need to find the slope between those 2 points. Whoops, minus, minus. So we need to do, let's see, it started at 2 and it moved to 12, and it started at 0 and moved to 5. So that equals 10 over 5, which is 2. Woohoo! All right. Now it wants us to find the instantaneous velocity when t equals 4. So instantaneous velocity is looking at the derivative. So we do need to take the derivative of s. So s prime of t is going to be 2t minus 3. There's our derivative function, but we wanted to find s prime of 4. Now you could have just skipped that step and jumped right to this, but it's notes, so I'm writing a little bit more. So 2 times 4 minus 3, that's 8 minus 3, which is 5. So our instantaneous velocity when t equals 4 is 5. That's different from the average velocity. Average velocity is just looking at like slope. Same if we were asking for the average rate of change. If we want to find the acceleration when t equals 4, we need to find s double prime of t. So we just found s prime of t. That was 2t minus 3. So then s double prime of 4 is going to be the derivative of 2t, which is just 2. And then the derivative of 3 is just 0. So the s double prime of 4 is just 2. So it is 2. And its speed, acceleration, it is meters per second squared. That's one thing that I missed in those other ones. Let me go back and add that because I just saw this, because we do have units. So we do want to add those on. So this is 12 meters. The average velocity during the first 5 seconds is 2 meters per second. Oh, my face is in the way. Same thing when we are doing the instantaneous velocity, it's 5 meters per second. So while it was going at different speeds along those 5 seconds in the first one, its instantaneous speed at t equals 4 is 5 meters per second. Its acceleration is meters per second squared because we've taken the second derivative. So it's meters per second per second. At what values does the particle change direction? So that is when the velocity is 0, the particle changes direction. So we want to see when does that second derivative, when does the first derivative equal 0? So when does s prime of t equal 0? Well, let's figure that out. So s prime of t is 2t minus 3. So that is at t equaling 3 halves. So 3 halves seconds. Woo! Done. Where is the particle s a minimum? So we could plug this into our calculator and we could see what's going on there. But we could use this idea of derivatives. So if we think about earlier, it was going at a particular speed. It was all positive. It was going up, so it was speeding up, and then it's speeding up, and then it slows, and then it stops pretty soon, and then turns around and starts going in the other direction. So that is right here. When it changes direction, its distance is at a minimum. I think that's what I wrote. The acceleration is always positive. Here's that same thing written a little bit better. Position s is at a minimum when the particle changes directions at t equaling 3 halves. Position at that time is s of 3 halves, which is a quarter meter back. So it starts going backwards and then speeds up.